What we're going to be going over here are Lagrange multipliers, and we're going to look at these Lagrange multipliers in terms of a shadow price, and we'll be doing some gradient calculations, and we'll look heavily here on the visual perspective here on these Lagrange multipliers, and we're going to be doing them in terms of a production function, really what's similar to the Cobb-Douglas production function. So for our production function, what we want to do here is we want to maximize some profit subject to some spending or cost constraint. Okay, so for our production function here, I'm showing it broken down between our revenue portion over here and our cost portion over here. So for our revenue portion, I'm just showing some unit amount here. Say we receive $1,400 per unit of other product we're selling here, times some material, times some labor here, raised to some exponential amount. And for our cost portion, I'm just showing a unit cost here, $350 for material, plus $200 for labor here on a unit basis. And really, we want to, these are equal here, the revenue portion here and the cost portion, after we take our gradient or our partial derivative here. And remember, the gradient here gives us our maximum here that we're going to be looking at for our revenue and our costs. And really, we're setting those equal, and they're really going to be, they only differ by a scalar Lagrangian multiplier here. So after we take our gradients or partial derivatives here for our revenue, they're going to equal a partial derivative here for our cost portion here by the Lagrangian multiplier here. We take that Lagrangian multiplier here times our cost portion here of our production function. So looking at it visually here, just looking at this bluish curve here, or this bluish curve here with those red lines here, the iso lines, that is our production function itself here. That would be the entire production function we're looking at, our revenue here and our cost. So what we've done here, I should have went up here and looked at it. In our case, we're going to be looking at several different cost constraints here, but we'll look at our numbers here based on $40,000 here. That's the maximum amount we can spend here for our material and labor here for manufacturing this product. Okay, so based on that, this is what we came up with here. I'm showing, again, our production function, this blue curved here with those iso equal product lines here, those red ones. And then what we do here, showing that we have this cost constraint, and this is sort of this kind of wire frame here with those blues here. That's our cost constraint here. That was that 350 M plus 200 here for our labor here. So what we did is, when we take those partial derivatives and we come up with our gradient, we come up with we're going to be looking at the maximum amount here we can produce here based on that cost constraint, and it's showing it right here. So that's the idea. And what we have here, you're going to have two different gradients. You're going to have your cost gradient here, that partial derivative here, plus your revenue gradient here. And they are perpendicular and parallel to these iso cost lines. So I'm really not showing them here. I got this yellow curve in here. That's the iso line here, and that represents the solution to the problem here based on our $40,000 allotted here. Okay, so that's our production function here, kind of broken down between, understand here, the mesh portion is our cost, and then the revenue portion here is the other part of our graph here, plus our iso line here based on that $40,000 we have available. Okay, so this is what you do here when you're moving over here, looking at these two different vectors here. Now I have these vectors scaled down here. I got the cost constraint here is shown as a lesser size here than the revenue or the output here. But nonetheless, you're going to have, it depends on what the Lagrangian multiplier is here. So what you have here with these vectors here, we're going to have these yellow ones here. They represent a material here on one side and labor here on the other side. And then this red one here, that's our revenue or output here. It's really a directional derivative here, but we're not going to get into that here. And really the difference is here, I'm showing again our cost constraints a little smaller here than our revenue output here, but it could be just reversed here depending on what that Lagrangian is here. I'm just showing them less here. They could either be, what the point is here, your cost constraint and your revenue, they can either be equal to 1 here. When we talk about that Lagrangian here, what we have, that scalar difference between our cost here and our revenue, that Lagrangian here, which is really an artificial variable here, it can either be less than or greater than 1 depending on our constraint. So if our cost constraints was greater than our revenue, then we would have, it would be reversed here, and then what we would be doing is just, again, taking your scalar difference here, or the scalar amount here, and we'll look at that here. So that's what we're looking at. These this revenue portion here, our revenue output would represent this blue, our blue portion here to our production function here, and this cost constraint here really is shown here by this, what we're coming up against, our maximum amount of available that we have in our budget for our cost here. Okay, so going back, and let's just look at some arithmetic here. So what you would have to do with this Lagrangian, you have to set up a Lagrangian equation here. I'm showing the revenue portion here, and then we subtract from it the Lagrangian multiplier here times what we have here for our cost constraint, the material and labor here, and then we have to throw in the budgeted amount, or what we have available here. So you can see what's going on here. Minus, in this case, we're looking at that 40,000 here. So just understand the Lagrangian. We're not going to go through the solution here. All you would do here in this case, you take, we'll look at the gradients here below, or partial derivatives, but all you would do is you take the partial derivative in terms of material, labor, and your Lagrangian here. And whatever comes up, you set them equal to 0, and then you can solve you have 3 variables, 3 unknowns, and you're going to be able to solve for the gradient or the maximum amount here based on a cost constraint. In this case, our solution based on that 40,000 cost constraint, I come up with labor of 78 point some points, our decimal points here for labor content, and material 69.68 again for material, and the Lagrangian multiplier here is 0.96608. So in this case, that Lagrangian is less than 1 here. Remember, depending on your cost constraint, that Lagrangian either can be less than a unit of 1 or greater than a unit of 1, or it could be equal to a unit of 1. Okay, so the first thing you would do here for your partial derivatives, just take it in terms of your cost constraint. Again, what you'd do here, Lagrangian times 350 and 350. I'm showing in an x and y here, but nonetheless, you come up with your fx here, taking a partial of that. You're going to have 350 times the Lagrangian multiplier, and then for your fy, or your labor content, you'd have 200 times your Lagrangian. So that is your slope here, or that's the slope here after you take your partials, 200 times Lagrangian, and for labor, material, 350 times the Lagrangian. So what you're going to do, this Lagrangian multiplier here, now we can determine our gradient. All you do is take your Lagrangian multiplier here times, in this case, the gradient here based on our partial derivative here is 350 times the Lagrangian plus 200 times the Lagrangian. So I just take that multiplier times each of those, the EX or the EM here, that's really a vector quantity, and then your other vector quantity here for EY or EL, the labor portion. Take that multiplier times each of those here, and this is going to be your gradient. So your gradient is going to equal, well, 350 times 0.96608 here is going to 338.13 plus 193 plus that times your 200 for your labor here, you're going to get 193.22. So we'll look at those over on our little layout here, but that's how you get to your ultimate gradient. This is where that multiplier comes into effect here. So if that multiplier was greater than 1 or 1, you just take it times whatever quantities you have here for your partial derivatives or your slope here. Okay, and then for moving down here to the revenue portion, I'm just showing that. So you take a partial in terms of your material and your labor. I'm showing at X and Y here. This is where you get your greatest output. Okay, so that's what you're doing here, and then plug in those quantities for that we solved here for Lagrange, 78 for labor, 69 for material, their decimal fractional amounts times, and then you're going to get this here. These are the slopes you're going to get. X slope 338, Y slope 193. So that's your gradient. So that's your gradient that you're looking at here. And you notice here, by using this multiplier here, taking our partial derivatives here for our cost portion here and the multiplier, we come up with our gradient here, and that gradient matches our revenue here. So the ultimate gradient here for our cost by that scalar amount equals our gradient here for our revenue. And remember, this gradient here, that's the path, or that's the maximum amount we can expect here from our production function based on taking those partial derivatives here. So that's how it works. So if we move up over here back to our scalar amount here, in this case, because they are so close here to that multiplier 96608, actually they would be very equal in size here, these gradient vectors here between your cost constraint here and your revenue or your output constraint here. I'm showing the cost constraint a little less here. And that, in the case here where I'm showing it a little less here, that is where you're going to have a lower cost here. You're up against the lower cost here depending on your production function. But nonetheless, what you're doing here is that scale, that Lagrangian here, that 0.96608 here, that is the difference. That Lagrangian, that scalar difference is the difference here. It's very little in the case here where we looked at that $40,000 cost constraint here. But nonetheless, it's that difference here, the difference in length here between those arrows, those red arrows that we have here. And nonetheless, and that's what we talk about the shadow price. That's going to be the shadow price. That's the price that you can afford to pay here depending on what your Lagrangian multiplier is. So that's what we're going to look at. So we'll continue on here just taking a closer look at our Lagrangian. Now looking at a top view here from our production function here that I'm showing here in blue, that's our production function, which includes both our revenue and our cost here. So what we want to be looking at here is a gradient path, and this is that red vector that we're showing here, and that's the path here of the maximum profit that we'd be looking at. We want to follow that path up here. And really, it's broken down between our material and our labor inputs here, and I'm showing them overlaid here for our revenue and cost portion here for both our material and labor here. Those yellow vectors represent our material and labor here, and both the revenue and the cost portion. But we're going to be looking really at the change in slope. But we're following this gradient path up here. That's the maximum profit that we'll be looking at here. So moving over here, a side profile of our production function I'm showing here. So this is our side profile here. So this is where we can get an idea of our different inputs here for material and labor. So at our first input point here, I'm really showing just 3 of them here. This is where we have really a low input for material and labor here, and what you can see on the side profile, this is where we have that our vectors going up here for really our revenue vector here. It's increasing at a fast rate, and then we get to this point that we're looking at, we're calculating here. This is where we're plateauing out here. We're coming up with that Lagrangian multiplier was 0.96 or something like that here. And then if we move down over here, you can see this is where our revenue would actually be going down. We have a greater input for material and labor here, but with the production function as it is, we're actually generating less profit here. So sort of a side profile and gives you an idea of what we're looking at here. Really looking at the change in slope here. We have an increasing slope. At this point, we plateau out, and then we have a decreasing slope. And based on that, we're having greater profits here, lesser profits here at some plateau point. And this is where we're looking at the change in the Lagrangian multiplier here, and we'll look at that. Okay, so if we move over here, I got it shown. I got the gradient path here. I've shown it out, broken it out here a little easier to see with these red spheres. That's our gradient path. And then we're really looking at 3 different points here, these blue spheres here. First point here, this is where we had a $4,000 cost constraint. We can only spend $4,000. Then we move up here, and this is where you see you have that real steep slope here where you're generating a lot of profit in this area here at a very fast rate. And then you get to your plateau point here. This is where we looked at that $40,000 cost constraint. So it's a flat here. We're not increasing or decreasing our profits here. We're just at a flat rate here. And then as we move down our gradient path here, we get down to a third point. I'm just threw them in here and just say that was a $100,000 cost constraint here. So you can see this is where we're nosediving, or we're going down with our profits here based on this greater increase here in material and labor that we're looking at. Again, we're looking at the change in slope, and it's going to be a change in our Lagrangian multiplier here. Increasing here, and as we plateau out, then we go down based on our production function that we have here. So then expanding on this $40,000 cost constraint that we've been working with, I'm showing it here, is that this is that blue ball here. So here's our gradient path moving up here. We plateau out, so you can see our revenue function here is pretty flat here for our material and labor inputs. So going up here and then plateau out, and then we go down. That's our gradient path. And this is where, again, where we're looking at that change in slope here. So at that $40,000 cost constraint, we come up with a Lagrangian multiplier here at, well, 0.96, approaching 1 here, a unit of 1. But we want to look at it in these terms here. So what you're talking about here, for every dollar input of cost, you're only getting out 97 cents here in output if you just round this off here. So that's what we're talking about, a shadow price here. So change in the unit output here depends on the slope. So what you want to do here when you're talking about that unit price here, so if you if you're going to put a dollar input in, and what we're saying is you're going to have to pay less than 97 cents here for this dollar input. You're going to have to pay less for it. That's what we mean by this multiplier here, or the shadow price here. So we're talking about a dollar in, but actually you're going to have to pay less than that. Well, I have to pay less than this your Lagrangian multiplier in order for you to generate any extra profit here. Okay, so what we're saying, the shadow price here, you have to spend less than that point than your Lagrangian multiplier, and we'll just put it in units of a dollar here. So it'd have to be spending less for an input here of 96.6, even though to get a dollar added output here. So, or that's to get that extra output that you're looking at, you have to spend. We'll look at the relationship there here. Okay, so going over here, I expanded it into a table here. So looking at, I got the Lagrangian multiplier shown here, and I'm only looking at this $40,000 cost point here. So we've got a Lagrangian multiplier going over here, and you're going to see that this is actually going down by some thousandths of a fraction here, going down here as we increase our cost constraint. We're going up from 40,000 by $100 each, 40,100, 40,200, 40,300. And at the same time, this is based on that production function that we have here. That's our revenue minus our cost here. This is the revenue that we're generating here. Here's our cost here, production function cost here, and here's the revenue that we're generating based on that cost constraint. So what we're going to really see here with this revenue here is that for every $100 we go up here in our cost, or we increase our constraint here on our cost, our revenue actually, it's only going up by $96 or something in that area. That's the only point we want to be looking at here. Input, $100 increase here, and our output is only $96.60. So it sounds a little odd here, but you can't pay $100 for your input here to get $96.60 out. It's not worth it here. But you're still making a profit, but you're making less of a profit. That's what I'm trying to say. That's our output here. And then our profit here, based on our cost less our revenue here, this is our profit. So at 40,000, we're sitting at $7,125. But as we increase our cost here, cost constraint by $100, you can see we're going down on our profit. So we're still making a profit, but we're making less of that profit. It was $7,125 down to $7,115. So make that point here. So again, shadow price, you want to spend less than 96.9660, or your Lagrangian multiplier for a dollar. That's the relationship. You want to get some ratio here. Just remember, you can't spend a dollar here to get, well, you can, but you're only getting 96 cents out here is what we're really saying. And then if we move over here, just looking at our multipliers here, I looked at those three different points. We have that $4,000 constraint. So at that point, my Lagrangian multiplier is 1.4622. So you can see here, for every dollar I increase my cost constraint, or dollar I put in, I'm actually getting $1.46 out here, based on that first point here in our production function, our cost constraint here of $4,000. So here's where we're increasing our revenue here at a faster rate, but And that's where the Lagrangian multiplier comes into effect. So for $1 in, I'm actually getting $1.46 out. Or $100 in, I'm getting $146 out at this point. So that's a good point to be at. Then we get to, there's another point in here where we actually have the Lagrangian at 1. And that's really, I think, a cost constraint I looked at. I think it was $33,000. Okay, so that's where you're going to get, that's where you get that sort of break-even point here. $1 in, you get $1 out based on a cost constraint, I think, of $33,000. Then we got to the point that we're looking at here, that $40,000 cost constraint. This is where we're only getting, for every $1 in, we're only getting 96 cents out here. And then moving down here, when we move down to this Lagrangian here with that $100,000 cost constraint, a Lagrangian went way down to 0.8119 here. So $1 in, you're only getting about 82 cents out here. So you're going to have to pay, the shadow price is this, you're going to have to pay less than 82 cents in essence to get any output here. I mean, to keep it level. You're making some, at this point, actually, when I didn't look at it, and we'll look at it in another example, this is the point where you're not making any profit here when you get down to that $100,000. That was our break even. That's where you're generating zero profits, I believe. So what you're really looking at, that change in Lagrangian, it's really a ratio of our input to our outputs to get the idea. So starting out here, we had a very high Lagrangian here multiplier, and that's where we're generating greater profits. Then we reach the, actually there's a point in here where your Lagrangian is equal to 1 here. And then you got to that point here that we're looking at, that 40,000, where a Lagrangian multiplier is down to 0.96 here. Again, this is the point here which you have to look at that shadow price. You don't want to pay more than 96 cents on a dollar to get some profit out of it. And then as we move down, our gradient path here, we got down to the point here, you can see the Lagrangian move down again. This is where we had that $100,000 cost constraint. Okay, so you can just see the pattern here, Lagrangian here, that it's really a ratio here that you're looking at. Start out here at 1.46, then we level off here, and then we're down to 0.8199 here based on our input. Okay, so that'll give you some idea what we're talking about when we talk about Lagrangian multipliers here and how they figure into, in this case, our production function.